Testing on Zoom. Can you guys hear me at all?
Yeah.
Yes. Okay, great. Okay, got it fixed. Okay, so as I was saying, there is a quiz. This is every Monday. This is a quiz for last lecture. You can find it on the homepage for the course website. And it'll be open until midnight tonight, but I want you guys to spend 10 minutes. If you're comfortable getting all the right answers in 10 minutes, that means you are picking up all the material that I want you to from the class. If you're struggling, then come to my student hours. I think today I have them 2 to 3. So yeah, definitely drop by in the Zoom. Okay, thanks everybody for joining. I'm gonna go back to screen. There we go. So here's the link to the quiz, and I'm gonna turn off my video. All right. Okay. Yeah, so if you're just coming in, we are doing quiz 2 for the first 10 minutes of class. It's on the course website, the link to it. So I encourage you to get started with it now. Try to get 1 submission in. Even if you get questions wrong, you have until midnight to learn about them and correct them. If anybody has any questions, like definitely like anything's confusing, feel free to speak up. Let's see. I suspect this slide might be useful. On an exam, I would probably give you this, so you don't necessarily have to memorize it, but you need to know how to use it. Yeah.
So this one, why would this one not be able to find us? This one can.
Yeah, so great question. There's a yeah, I'll show it on the quiz. So week 2 quiz, there's this question asking which of these can you not apply master theorem on? The question was, why can I apply it for this one, but I cannot apply it for this one? So this one you can use master theorem, this one you cannot. Anybody want to maybe explain why? Yeah, I see. Okay, so why can you use it here? Yeah. Right. So square root of n is the same as n to the 1/2 power. So that gives you the d. So the d is 1/2 for that one, right? And why can you not use it on this one? Huh?
since the n times log n can be written as log n of n.
N times log n. Oh, can you write it? The d has to be a constant.
Since
You cannot. Yeah. All right. Yeah, that's it. So n log n, there's not a way to write it as n raised to a power where the d is constant. Right? Whereas this one, you can write it's n to the 1/2. So your d is 1/2. Yeah. So that's why it does not apply for this one. I guess we can talk a little bit about this. Why does it not apply for this one? Yeah, you got two different subproblems. So you have to have a way where it's like, why does it not apply for this one? Yeah, Vince, yeah. Right, so for master theorem, you need to be able to, it's like n divided by a constant, right, b. So for this one, it's n minus 1. You can't write that as a fraction, right? You're only subtracting 1 each time. So there are a lot of cases where the master theorem doesn't apply directly. You can like rewrite this to like upper bounded, or you can do like funky stuff to make it work, but it wouldn't work directly. Yeah, so the fact that you have the n minus 1 kind of, it has to match pretty exactly to what the theorem says for it to work. Yeah. But that is what you would do if you were trying, like, what you can do is you can put it over 1, and then you can upper bound this by just n. And then you would get like a slightly worse, you could do that to be like, well, this recurrence is smaller than this other recurrence where I can use master theorem. So then that does also give you a big O. But it's like, but yeah, that's basically maybe what you would do for some of these that don't work. You could try to upper bound it. You know, even for this one, you could say like, well, you know, I recurse once on n divided by 5 and once on 7n divided by 10. You could say, you know, like that can't be worse than recursing on 2/10 plus 7/9. Like it can't be worse than recursing on 9n over 10 once. So you can kind of like upper bound it that way. Yeah. Cool. Okay, so I think that's the time for the quiz. But yeah, if you guys have questions like these, like definitely, like, I don't know, maybe I'll try to do videos and share those with you where I like discuss the answers to the quiz or something. But yeah, but also like come to student hours, or yeah. If you have questions, you can email me. You can post on Piazza, and then you guys can help each other out. But that you do want to like understand why the answers are like a certain way. If you think if you think one of the answers is wrong, that could also be the case. So definitely like email me or bring it up in class. All right, cool. But let's get started with lecture 8. All right, so everyone, welcome to class. Homework 2 is due tomorrow at 11:59. There is a homework 2 walkthrough that I put together. I think I shared the link on Piazza, and I think it's also on the course website under the homework. So this is a 30-minute YouTube video where I just kind of walk through the homework and then give out a couple of hints here and there. So if you're struggling, you can take a look at that. It does cover a little bit of the coding, but for the very last one, I don't do any code. I do pseudocode. So obviously, if you're struggling, then you can always come to student hours. If not, take a look at the walkthrough. Quiz 2 we just did. It's due at midnight. Again, always retry, but generally speaking, if you feel like you know the content on the quizzes, that's probably setting you up for success come the midterm and the final. If you're just guessing and that's how you're getting good grades, then you probably want to like take a closer look at some of the questions, try to understand them. I will try to post like videos explaining each question for all the quizzes we've done when I get a chance. Cool. So we're back. We are going to continue what we were discussing last time. So we're actually going to introduce this median of medians divide and conquer algorithm. We're going to analyze the running time. And then we're going to introduce a new section of algorithms called randomized algorithms. And we're going to cover mainly one called BOGO sort today. Next lecture on Wednesday, we're going to start covering quicksort. So the randomized algorithms, you might already be familiar with some of these. I think the main focus of our class is going to be to actually talk about how to analyze randomized algorithms to know the running time, for example. How do you guys have a prerequisite for taking statistics? So no one has ever taken like if I say like expected value of a random variable, that like probably doesn't mean much to people. Like if I talk about like Bernoulli distributions or something like statistics courses, zero background. A little bit, but mostly zero. Okay. I will do my best to try to introduce you to the stuff that we will use to analyze randomized algorithms. But yeah, that's definitely, again, like I guess one of the reasons computer science can be a little hard is because it does build up on a lot of other stuff. So I will introduce what you need to understand what we're talking about. But if you really love randomized algorithms, you probably want to get a more solid background on statistics. Okay, cool. So from last lecture, this is the pseudocode that we wrote for the select AK problem. All right, if you guys remember. Yes, this seems familiar to everyone. We've got our base case. You should always have a base case in a recursive solution. We pick a pivot, we partition the array, and then we have our recursive cases where we call ourselves on either the left side or the right side. Yep. Okay, so this is from last lecture. I think last lecture as well, we covered what was like, is good enough, when is good enough good enough? So we talked about how ideally we would like to split the input in half, and that would actually give us a running time for this algorithm. If we can guarantee that these sides are split in half, then we recurse once on an array of size at most n over 2. So it gives us a running time by master theorem of O of n, right? That's what we talked about last time. But then we also talked about how we actually can't do that. So picking the exact median, the exact middle of the algorithm, is not something that you can do in linear time for an arbitrary array, right? So we talked about, hey, what if we don't get exactly the half of the array? What if we're a little off? Maybe that's easier. Maybe it's easier to pick a number that will split the array into 3/10 and 7/10, or something that is not half and half, right? The ones we're going to use is 3n over 10 and 7n over 10. So now our goal is I don't want to split the array exactly in half. I want to split it so the left side is at least 3n over 10 and the right, and at most 7n over 10. All right. And we haven't talked about how to do that. I did mention that if you pick a pivot randomly, in practice, that does really well. But it can do poorly if you happen to pick the wrong random pivots, right? Master's theorem would say that this is O of n. I think we finished covering this last time. So this is mostly review. So now we're actually going to talk about how to do that. How can we guarantee this, that the two sides are between a certain range? Yeah, so it would be still good if we do it. So again, our goal is we need to find a deterministic way, so we're not going to use randomness, to pick a number from an array that is not sorted such that we can guarantee that each side is at most size 7/10 of the original array and at least 3/10. Okay. The solution here is you use divide and conquer again. All right. So again, a little bit of review. We said, why can't we do this? Why can't we just pick the median? So this would give me the median. Why does this not work? If I just say, let me call myself recursively to find the median. Yeah, so you'll notice that the problem size itself does not shrink. So our base case has to do with the size of A. Because we're not making it smaller, this means it'll just run infinitely. So that's why we can't pick the median recursively, right? Instead, what we're going to do is we are going to use recursion. We're going to pick a median, but we're going to pick a median of a different array where we will guarantee that it will be smaller than A. Why will that work? Why is it so? In general, if you're using recursion, if your problems are getting smaller, you can sort of assume it'll work. As long as you don't skip over your base case accidentally or something like that. So if you're like decreasing by 2 and your base case only covers n equals 0, you might accidentally go all the way to -1. And then you're like, oh, then it just goes on infinitely, right? So you want to make sure, but that's essentially what we're going to do. This helps because it means that we can use recursion. So as long as we can find an array B that is smaller than the array A, it doesn't have to be, and it has to be smaller by a fraction for the running time to work out. But we'll cover that technique. Yeah, so basically the question you want to have in your mind is like, how can we do this? So we don't actually, we're saying it's okay if we don't get the median of A, but is there another array that is smaller than A, but contains some of the elements in A, that will help us, where if we get the median of that array, it'll be pretty close to the median of the original array. Okay. That's actually like probably the more clever part of the algorithm, but any ideas? How you could, yeah, sure. How you can make a smaller array such that if you take the median of that array, the answer is pretty close to the median of the original array. Sorry, what was that? Oh, so you're saying like, let me just drop the first element and then call myself on the median. That actually does work in terms of your algorithm will be correct, but because your array is shrinking by 1 each time, the running time is really bad. Yeah. Okay. So the idea that somebody came up with, I think in 1973, I think these were some researchers either at Stanford or like MIT or somewhere, okay? It's something called the median of submedians. And they argue that the median of medians is close to the original median. So what does that mean? That means if I take an array and I split it into smaller sections, I'm gonna call each of those a submedian, or you can call it whatever you want, but essentially I take my original array and I'm gonna split it into small sections, smallish, okay? We're gonna figure out exactly how big they are in a second. If I take the median of each of these sections, I'll get a smaller array that is, so for all of these elements, I'll get 1 element, right? And for all these, I'll get 1, right? So I will get a smaller array of elements of A. And then what I do is I take the median of those elements, okay? And the median of submedians is what we're going to use as the pivot. Yeah. Yeah, so we are going to walk through an example. Like, yeah, we're actually going to walk through an example, but essentially the idea that they had is I can take my original array and split it into chunks of 5, okay, of length 5 each. And what I'll do is for each of those 5 elements, I will calculate the median of those 5 elements, okay? Now, the key there is because each of those elements, I will make sure that each of the chunks is at most 5. It doesn't matter what algorithm I use to calculate the median. It'll be constant time because my input is fixed. It'll be at most length 5. So calculating the median of 5 elements is constant time, okay? I'll do that for each of the chunks. So if this array is size 25, I'll have 5 chunks of size 5 each, okay? So at the end, I'll have 5 numbers, which are the medians of those chunks. And then what I'll do is I'll calculate the median of that array using myself, my recursion. And the reason that works is because this array is going to be 1/5 the size of the original array, right? And the I guess not the clever part, but the part that you need to be convinced of is if I do this process, the median of these values is going to be pretty close to the median of the whole thing, right? So we argued before, hey, we don't need the exact median, we need something that's close. And this is a process to get something that's close. So you need to, we're going to walk through it, but we're going to need to convince ourselves that it does actually give you a number that is pretty close, okay? This is the ideal pivot. This is what we would want to use. We're going to use this one, and we're going to argue pretty close, okay? So again, we're walking through an example. So choose pivot of this array A. This is the array. This is my original array. Again, it's not sorted. So how does choose pivot work? Right. So the first thing it does is it splits A into groups of size at most 5. So the reason I have ceiling here is, if you have a little bit left over, right? So if you have 26, you'll have 5 groups of 5 and then 1 group of 1. Okay. So it says there's m groups, n divided by 5, each of size 5. So that's the first thing it does. So we would do this. So somehow in code, or like you would keep track of it. Actually, the easiest way to do it in code is you iterate, and every time you hit an index that is I mod 5, you'd be like, oh, get the median of this. And I'll show you guys an implementation that does that. Now for each of these, so from I equals 1 to m, so for each of these splits that we've created, we will find the median of that split, right? So in this case, that would be the median of 1, 3, 8, 9, 15 is 8, right? This is the middle number of those 5. And you do the same thing for this, same thing for this, same thing for this, same thing for this. Now, what is the running time of finding the median of each of those numbers? Like what is the running time of finding the median of this array? Yeah, O of 1, it's constant. That's exactly right. This takes O of 1 for each group because the groups are at most size 5. So it literally doesn't matter. As long as my algorithm terminates, it doesn't matter what I do. It could be some crazy, I could sort it, I could do the n squared one, I could do whatever I want. But because it's at most 5, it's constant. All right. Now we're going to do that for m groups, right? So the total running time of calculating all these medians is going to be O of 1 times m, because there's m of them. So it's going to be O of m, right? But m is essentially n divided by 5. So it's O of n, all right? Does that make sense? That the running time of this for loop is linear in the size of the original array. Okay. And then what we do, like we said, is we actually call ourselves recursively, not choose pivot, but like our original function on this new array of medians. So this we'll call ourselves on 8, 4, 5, 6, 12. Okay. And this array could be like pretty big. There is no fixed size. It could be, it's whatever the original size divided by 5. So if the original size is 1 million, this array would be, 200,000, right? But we just call ourselves recursively, and we assume it'll give us the right answer because we assume that our recursive algorithm is right, right? That is actually called the, I think they call it the recursion leap of faith. Anytime you're dealing with recursive algorithms, as long as you're calling yourself on a smaller version, it makes it a lot easier to code the recursive algorithm if you just assume that your algorithm already works, right? And then at the end, we just return. So the only tricky part is here we're going to get 6. And our algorithm is actually going to tell us, okay, this is, this is the 4th element in this array. The slightly tricky part is you need to take this and then tell me what is the index in the original array, right? So tricky in terms of like implementing it, like writing the code for it. But that's what this is saying. So eventually what this does is it's going to return this 6. All right. So this is a pretty complicated way to pick a pivot. What I would recommend in practice is you pick one at random, and it works really well. But this is the deterministic way to do it. That also works pretty well. Any questions on this so far? Well, so this is called a median of medians. You can actually use this technique on quicksort. So if you guys are already familiar with how quicksort works, you can actually make quicksort deterministic, where its worst case running time is going to be n log n by using the same technique. We'll cover that next lecture. But if you already know how quicksort works, you can kind of maybe think about how you might use this to make that not random. Again, in practice, random is good. It's actually usually better. Okay. And then what we do is the next step. So this is outside the choose pivot, right? The next step would be, now that we picked our 6, we have the left side and the right side, where the left side is smaller than 6 and the right side is bigger than 6. But note, these are not sorted. We're not sorting them. Okay. We're just putting them one side and one to the other. So all of this takes linear running time. Does that make sense? This is probably the trickiest part of the code, or like of the algorithm. This is probably, I mean, they wrote a research paper on this technique. So it's like at least in the 1970s, it was not obvious to people how to do this. So you should not expect like, oh, I ask you the question and you'd be like, well, I've never seen that before, but here is like a way to do it, right? This is some researcher somewhere, PhDs, figured it out. And now you're supposed to know it because it is now known, right? It actually works. So here's some code that I ran on random arrays to pick the pivot. So if you pick the pivot, this is the index that ends up getting picked. If you pick it randomly, this is basically a uniform distribution. This is like the number of times that index 20 got picked. If you do it randomly, it's basically uniform. If you do it with this pivot method we talked about, most of the indices you pick are, you know, between 38 and 58, most of them. And that's kind of what we want. We want a pivot that picks the index in the sorted array that is close to the median. So the median here would be 50. If we always picked 50, or if we always picked the 50th smallest element, then that would be ideal because it splits the array in halves. But with this method, you know, we don't always get the median, but we'll get close enough, right? So this is like empirically, if you didn't want to prove that you actually, that it's always right, you could write code for this and like plot the graph and be like, well, see, it's pretty clear that most of the time it's really close to splitting the array in half. Okay. But we can also prove it. We can show using logic and mathematics that the left side will be at most 7/10 plus 5, and that the right side will be at most 7/10 plus 5. Okay. In the lecture notes, there's a proof using like writing it out and talking about it. In lecture today, we're going to cover a proof by picture. So I do encourage you guys, anytime you don't understand something, draw it out. Like that's how I learn algorithms. Like draw the trees, draw the step-by-step things, and like just draw it out, try to understand it. So here's our proof by picture. This is, imagine this is an array where it's like 1, 8, 9, 3, 15, 5, 18, right? So imagine it's just a single array altogether. Now, the first thing we do is we split it into m groups of size 5, right? So this is in our head, right? We're just imagining this is how the algorithm works, okay? So there are, you know, n over 5 groups or thereabout. Now, in your head, so this is not what the algorithm does. It doesn't have to do this, but for our proofs, for like why the median will be close to the actual median, right? Or basically what we're trying to prove is that the left side is going to be at most 7/10 of the total array. So in our heads, what we're going to do is we're going to sort each of the sections. This is not what the algorithm does. This is what you would do to convince yourself the algorithm works. Okay, so this is what happens when you sort them. All right, so this is the original array. You sort them, they look like this. Okay, this is all in our heads. It is not what you would code. You wouldn't code this up. Then what we do is we sort them by the medians, right? So here we sorted each group of 5. And then what you can do is you can sort them by the medians themselves, right? So this group gets moved over here because the 4 is the smallest, right? So I am not sorting by 2 or 3 or 13 or 70. I'm sorting by the median, okay? Now this is what the groups look like, all right? Now this is what my algorithm is going to return, this number, right? It's going to return the median of 4, 6, 7, 8, 10. So again, the algorithm is not sorting. It's not doing any of that, right? The algorithm has these arrays to work with, okay? But in our heads, we sort them, then we sort them by the median, and we say, well, our algorithm is going to return this 7, okay? So one question you can ask is, well, I guess I didn't put it in the slides, but essentially, how many numbers are smaller than 7? So how many numbers do you know for sure are smaller than 7? 6, right? So, or the whole entire array, of the whole entire array, you know, yeah, you know for sure 4 and 6 is smaller than 7, but the I guess the thing you realize while you're looking through these pictures is that that actually gives you a little bit of extra information. It actually tells you that whatever these numbers are, I don't know what they are because I never looked at them, right? Our algorithm never looked at them. We sorted them in our heads. Our algorithm does not look at them, but for sure they're smaller than 4. And we know 4 is for sure smaller than 7 because our algorithm did look at this, right? So that means that these 3 have to be smaller than 7, right? That also means these 3 have to be smaller than 7. Okay. So at least, okay, you also know that the 6 is smaller, but at least you know these are smaller. All right. Now, this is a specific example, but if you think about it more generally, you have m groups, okay? For half of them, or like for m minus 1 divided by 2, or m divided by 2 minus 1, for about half of them, half of those groups are for sure smaller than the median that you picked. So it's this example, but now we're talking more generally. So instead of having 5 groups where 2 of the groups have 3 elements smaller, in the general case, you can make the same argument to say, well, if I pick the median of my medians, right, m divided by 2 of the groups will have 3 elements each that are definitely smaller than my median. Right? That makes sense to folks? So you write that out in math, and you get something, essentially, there's a -1 because I'm not counting this one, and then I put a -2 just because there might be like an array that is like has like leftovers, right? So it doesn't have to be exact, but this is the formula where you would say like at least these many elements are smaller than the median I pick. Does that make sense to people? Because there's 3, this is the number of groups that are definitely smaller, right? It's the ceiling of m divided by 2 -1 because I'm ignoring this group, okay? So I divide by 2 to cut it in half, and then I ignore the middle group. And another -1 because you might have a leftover group, okay? So we're just trying to get it. This -2 doesn't actually matter. So if you thought that was 0, that's fine. It doesn't actually end up mattering. But I'm just trying to get like an upper bound, essentially, on how many elements are smaller. So this is the number of groups that you know for sure are smaller than the median of the medians. And then for each group, you know for sure 3 elements are definitely smaller, even though you never looked at them. So that's why it's 3 times and then this function. How do you guys feel about that? A little iffy? Okay. Again, this is probably not going to be on the exam, but this is how you would try to prove. You need to convince yourself, okay? So now we know that for the median of medians, right? We walked through a specific example, but now we know that for the algorithm we described, which picks the median of medians, there are this many elements that are definitely smaller than the median, right? So how many are larger? You take n-1, which is the total number of elements, not counting the pivot. And then you subtract what you know for sure these are smaller. So now I'm asking how many are larger, right? So you take the total minus the number that are smaller. That gives you how many elements. At most, this many elements are bigger. So if you work out the math, m is n divided by 5, right? So this becomes n divided by 10. And then this is a ceiling operation. You can actually drop it because you're trying to upper bound it. So you could just say n divided by 10. And then if you multiply -3 times -2, you get +6. So that's where the +5 comes from. And then 3 times n divided by 10 gives you 3n over 10. And then n minus that gives you 7n over 10, right? So we're simplifying the math. Right. So now we know both at least how many elements are smaller, and at most how many elements are bigger. Right? And that's all we needed to know. So we actually we proved this part. We proved that the right side is going to be at most 7n over 10 plus 5. Because by the argument we just walked through, the way we picked our pivot, there will be at least around 3 over 10, 3/10 of the array will be smaller, which means at most 7/10 will be bigger, right? We have the plus 5 because there's like some, you keep track of it, but it actually doesn't matter in the running time. You actually end up dropping the plus 5. So, it's whatever. By the same argument, the left side is also at most. So you use the same argument, but you ask the opposite question. So you're like, how many elements are bigger? That gives you a lower one, and then you subtract that, but it's exactly the same argument to get the first part of the proof. Okay, so that actually proves, I guess, that the way we pick our median guarantees that our left and right side will never be bigger than this. Okay, and you'll notice that's actually why the groups have to be of size 5. So a challenge question for you, if you want to challenge yourself, would be when the algorithm told us make groups of size 5, what goes wrong if I make groups of size 3? Right? Because it was kind of important that we had at least 3 elements smaller. So if you do want to challenge yourself, you can think about like, hey, what if I make the subarrays be of size 10? Would that work? What if I make them be of size 3? Would that work? And there are numbers where it doesn't work, and there are numbers where it does work. So that's why it's important to not just know the implementation, right? So somebody could just tell you, split them into 5s, right? But you might be like, well, I think 5 is too big. I want to make my algorithm faster. I'm going to split them into arrays of size 3. And then actually, you make the algorithm slower because the proof doesn't work when you use arrays of size 3. So that's why it is important to kind of like try to understand where things are coming from. Cool. That is the main content of today's lecture. And we can actually see in practice, this is 3/10 and this is 7/10 of 100. So actually, most of the time, it picks even smaller bounds. But the math just gave us an upper bound, right? It said like, there's no way you will ever see a number that is outside this. No way. No matter how many times you run this median of medians, there is no possible way you will ever see a number outside of that. All right. In practice, most of the numbers are actually a little smaller. They're like, it looks like 4/10 and 6/10. So they're actually a lot closer to the median in practice. Okay. Cool. So that's it. Now we're going to talk about the running time of our solution. So suppose the lemma is true. It is because we just proved it. So that means that the left side is at most 7/10 and the right side is at most 7/10. Then what does our recurrence relation for the algorithm look like? So our algorithm, T of n, what is the recurrence relation for our algorithm now? So we have proven that the left and right side will be at most 7/10. So what does our algorithm do? It does for sure, it calls itself on the left or the right side, right? Yeah. It will not call itself, well, it does call itself twice, but not on same sized inputs, actually. So for sure, it calls it, well, I wonder if I put the pseudocode here. Oh, yeah, I did. OK, so yeah, why don't you guys think for 2 minutes and try to figure out what the recurrence relation is. Here's the pseudocode. So this choose pivot, if you remember, this calls ourself, right, on an array of some size. And then we also call ourselves once, only once, because these if statements are exclusive. So either on the left or the right. So what is the worst possible recurrence that you could get? And yeah, I'll let you guys think about it for 2 minutes, talk to each other, try to guess. So this is like select, and it calls itself on that B, that median of medians. And then we have this either on the left or the right side. Oh, yeah. And this is what we proved. We proved that the left is at most this big and the right is at most this big. We are, oh, we use it for the base case, but this can be anything because it's constant. So you could put it to be 1. Most of the time when you actually implement this algorithm in code, people tend to pick bigger constant values because it turns out that all this stuff is like super complicated. So if you do it, like if you're always doing it for like, because the tree kind of gets bigger as you go down. So if you do it for all arrays of size 2, it's like a ton of extra work. So, and compared to merge sort, like the running time, the big O does not change. But in practice, people will pick a bigger value of the base case just because once you have a small enough array, merge sort is like pretty darn fast, where you don't even bother doing this like divide and conquer. So the total algorithm is O of n. In this specific situation, merge sort is always n log n, but your A in this part is at most 50. So this is always O of 50, or like O, this would be like at most O of 50 times log 50, which is just a constant. So this is O of 1. Right. Yeah. 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 So in the base case, and you can actually do whatever you want. You can use insertion sort, which sometimes is better than merge sort. You could use like, you could write some random code as long as it terminates. That does not affect the big O. Cool. All right. So what did you guys come up with? What is my recurrence relation? Anybody? Yeah, right there. So T of n is less than or equal to. Okay, so he says T of n over 5 plus T of 7n over 10. Okay. Plus O of n. Is that what you guys got as well? Do you see, does somebody want to explain where each of these are coming from? Somebody else want to explain? Yeah. Okay, got it. So somebody's saying this n divided by 5 comes from when I call myself on the array of medians, right? So if you look at the pseudocode, when I call choose pivot, I create a smaller array that's a fifth of the original size, and I call myself on that. So that's where this comes from. Where does this? Yeah. Yeah. Put it back. You do. Sorry. It would be. So you think this should be? Oh, like a 5 here. It does not call itself 5 times. It does break up into groups of 5 each, but it actually just calls itself once on those medians and medians. Getting the median of the smaller groups is actually all in this part, where it's like it's basically constant time, but like to get the median of all of them is linear time, and then to like put everything back together is linear time, and like basically everything you do, there's like a bunch of places where it takes linear time, but that's all just encompassed in the O of n, right? Yeah, so this is the array of medians, and this is the recursive call, where you either called yourself on the left or the right. And we showed that that was at most 7n over 10, right? So this function, I don't know if you guys remember, because I guess we did it last week, but what is the running time of this recurrence relation? You actually cannot use the master theorem here. But last week, we actually walked through this exact recurrence relation using the substitution method. And we showed that it was O of n. Now, an intuitive way to think about why it's O of n is because here you might be, you're calling yourself on two sections of the array. You might be like, there might be some overlap in the numbers you call yourself in, right? But at most, this is 9, this is at most t of 9/10 plus O of n. So it's not equal to this because there might be some overlap between the elements, but it is at most this. And big O is an upper bound. So by the master theorem, this is O of n. Okay, so you know that this is at most linear. The substitution method you can use to prove it is exactly linear. But yeah. The A value for this would be 1. Yes, A for this would be 1. B would be 10 over 9. And D would be 1. Right? Because, 9/10 is like, you might think the B is 10, but you have to do that thing where you like 9n over 10 is like the same as n divided by 10 over 9. Yeah, so you do want to make sure, like you want to make sure the B, like it has to match where there's like a single n on top. Like the master theorem, you got to make it look exactly like it looks, right? Yeah, so, and then that gives you that, like, this gives you that, that A is smaller than 10/9, or then it's smaller than B to the D, because B is this and D is 1. And then by that case, it tells you that the running time is going to be big O of n to the D, and D is 1. Yeah. Yeah, so we did that. So again, let's just summarize before you guys head out. So first, we thought about the best possible pivot, okay? And if we could find the median, we argued the running time would be linear. Then we said, if we don't get the best possible, what if we get something that's good enough? And that's where we came up with this median of medians. And again, it's not something that you would necessarily come up with on your own, except now you know it, so now you would come up with it. But this is something that, like, there's a research paper where somebody like came up with this idea and proved everything that we showed. So the very first time you come up with something, it's very hard. But once you're like, now you guys should, if you ever have a problem where you're trying to pick the median, you can say like, well, median of medians should give me something close enough. Okay. And that's it. So for next lecture, we're actually gonna, yeah, that's basically the end of the lecture. Hopefully the pace was good. Next time we are going to cover quicksort. So, and we're going to go more into randomized algorithms. I will try to give you guys the background you need in statistics to analyze them. But if you have time and you can look up expected value, that might be helpful at next lecture. Cool. Yeah. Yeah, what's up?
When I was originally on 280, I actually found this video that helped me. I don't know if you've seen this or you were going to add it, but I can email this to you as well.
Yeah. Definitely email it to me. Yeah, that'd be great. I'll try to put it in the course. Yeah, any videos that help you out.
Are office hours the same, 1:30 to?
We have actually permanently moved them from 2 to 3. Okay. Because the TA office hours are.
So I usually can't make it to those.
On Fridays I have them 3 to 4. And on Tuesday, Thursday, I have them 3 to 4. Okay. Yeah. So it says Monday, Wednesday at 2 to 3. Got it. Okay. Yeah, we can email me when we can schedule something, or post on Piazza if you have like a specific question, and I can try to help. Yeah.
I thought you said for this one, we're going to use master theorem.
You can't, right? So the original recurrence, you can't use master theorem directly, but you can do this thing where you say, well, it's at worst this recurrence. And for this one, I can use master theorem. So really master theorem is, we are using it to give us upper bounds, but really it's a lot stronger. It gives you the big theta. And in that case, like this wouldn't work at all because you don't know that, like the only thing you know is that this recurrence is bigger than the other one. You don't actually know that they're similar because you can't just like, all I did is I added these things inside. Yeah, because there might be some overlap. So the other one could be a little faster, but you could do something where you like, there are things you can do, but it just like directly, you can't use master theorem, but you can use it to get like a guess. And then what I would do is I would get this guess, and then I would use substitution to prove it, quote unquote, if you still wanted to. Yeah. Yeah, what's up, guys?
So I have a question on the pillars of the homework.
Yeah.
It's
Okay. Yeah.
So it was the second part of the homework.
Yeah. The pick berries. Yep.
Yeah, pick berries. So for the test, I did the same thing that you did in the pseudocode in the video.
Right.
But the test cases that you have in Brace code, there's one that like goes it skips like 4 different like berries to pick. You know what I'm saying?
Yeah. Yeah.
You know what I'm saying? So I don't know how to code that. I've done the test case for picking, like skipping only 1 and skipping 2 and skipping 3, but that's kind of like
so you should not be doing all of the cases. So the only 2 base cases you need if you're going to code it in the pseudocode is the if you have an empty array, an array with 1 element, and an array with 2 elements. That's it. The rest should be handled by the recursion, because you should never be dropping in a single recursion, and like in a single step, you should never drop more than 2 elements from your array. Like you should, in your head, you should do this. Like there's a video I'm going to share that somebody shared with class. There's this thing called the recursion leap of faith. So you don't have to like do all the work. You should assume that if you're calling your function on something that's smaller, just stop there and be like, this is going to give me the right answer. Whatever the answer is, this call is going to give me the right one. And all I need to do is just like whatever extra little step I need to build it up to my original input, right? So if you're already calling yourself on like an array of size, 2 smaller, you should never need to call yourself on an array of size 3 smaller, because you should be like, this 2 smaller array, that is going to be the correct answer. It is going to tell me the maximum number of berries I could possibly pick for that array. And then you really only have 2 choices. Either you picked the first thing, and that means you have to get the maximum for, drop the first 2 and everything else, or you didn't pick the first thing, which means maybe you picked the second one, but you don't actually have to worry about that, because once you know you didn't pick the first thing, you can just drop that one and call yourself on the rest. And that, yeah. So I would try, like don't try to like expand out the test cases. Also, the base case might be a little tricky. I forget. Actually, I'm forgetting exactly. I'll try to clarify this on Piazza. There is one open question, which is like if you have negative values in the array, there is one implementation that's recursive that picks, if it's only a single negative value, it picks that one. But in theory, you might like that. Just that depends on the problem statement. Like, is it do I always have to pick some berries, or can I choose not to pick any if it's negative? Yeah. But I'll try to clarify that on Piazza. Yep.
If we use a variable,
yeah, it's fine. The whole thing, like, don't use equals. Like, that's mostly like don't worry about that. I probably should have dropped it from the assignment. I just want you to implement it with recursion. But so like, yeah, you can assign things. Because assignment is not like, I think the equals thing is like, there is a way to implement it where like you never assign anything. And you're just like, it's like 3 lines of code. You're just like calling yourself, and you do like 1 plus this, and then you put like standard max, and you take the max of those. But I don't think that's like important. The important part is the recursion. Yeah.
Is it possible to have the lecture for next class?
Yeah. Yeah, I know. I'm a little slow. I'm putting up the lectures. I will try to put that up today if I can. I am usually coming up with most of these like a few days before. But yeah, I'm like halfway through next lecture. So I think if I can get it done today, I'll just put it up on the site. Yeah, to get it before class. Because yeah, I do want that to be the case. Where like, I guess like my ideal situation is all the lectures for the week are up before the week starts. But I'm still trying to catch up there. Yeah. Yeah.
As a part of the vector function, was trying to like divide like the sun.
Right.
And then I couldn't find a way to do it.
Yeah. So the easiest way to implement it is just you make copies of the vector. I don't know if somebody asked on Piazza about this. I'm not sure if that was you. Yeah. So it turns out the big O running time if you copy is like not different, but it is true that it is slower. It is a slower algorithm if you copy every time. Normally what you do in C is so the way I wrote the function, I think the vector is like a const ref, so you can't modify it in place. So what you could do is you like pass essentially the start index to the so it's like you keep the same vector, but then your function also knows like where it's supposed to start. So instead of, but yeah, that's basically it. And so it always gets the same vector, so you never copy it. But instead of like the vector getting smaller, it's just like you have this extra parameter that is like, I should start at the 5th index, and then your function is like, okay, that's the start of my vector, even though I got a bigger one. Yeah. Then you don't always need a helper function. You can use default parameters, but yeah, helper function is fine. And that's actually. You can do it in many ways. So I think the easiest implementation does not need a helper function, and it's the one where you actually just copy the vector. Like if you're like, I'm going to drop the first thing, you just make a new vector that has everything except the first thing, and then you call yourself. And that's like the easiest, most direct from the pseudocode. But it turns out in big O, it is not slower. They're both n times 2 to the n because you're calling this recursion. Later in class, we'll learn about dynamic programming, where that actually makes a solution for this problem possible in, I think, O of n time and linear time. So it's really good. But for this one, you don't have to worry about it. And then, yeah, I think that's the easier implementation. That's fine. There is a more optimized implementation where you're not copying the vector, where you probably need a helper function that takes in an extra parameter that specifies the index of which you start instead of copying everything. Yeah, and that's fine too. That's actually, in practice, that's faster. In big O, there's no difference. Yeah. All right, see you guys on Zoom.